My name is John Thornton,
And I'm Adam Kwan.
and we are presenting the paper of mechanical and thermal properties of cement composite graphite for solar thermal storage materials from the journal Solar Energy. The presentation is laid out in the why, the how, and the findings.
So for the why, we're looking at solar powered power plants, or like solar thermal power plants. And because there's a lot of fluctuations in the weather, due from sunny days and cloudy days, the systems required are thermal energy storage systems in order to have a consistent flow of energy go through that power plant. So the study looks at less corrosive and less expensive alternatives, such as aluminate cement pastes with various waters and cement ratios and graphite content. And then they would heat treat some of the samples in order to look at the thermal and mechanical properties. The overall goal is to have optimal properties in a substitute paste that can be used for future solar thermal material selection in solar power plants.
For the how, aluminum pure cement pastes were cast in different water to cement ratios of 0.3 to 0.4. From that, graphite was added in mass concentrations of 1, 5, 10, and 15%. The pastes were molded and cured for 7 days underwater at room temperature and then dried to 105 degrees Celsius for 24 hours before testing. An automatic pressure test machine was used to test compressive strength. The thermal conductivity constant tester was used to measure thermal conductivity constant and volume heat capacity. The thermal expansion coefficient apparatus was used to measure thermal expansion coefficient.
So these are the chemical reactions that were associated with the dehydration in the heat treatment process for the paste. In all of the equations, you can see there's water molecules on the left and less of them on the right due to the hydration or the dehydration of the heat treatment. So the C3AH6 decomposed after 6 hours in the heat treatment at 350 degrees, while the AlOH3 also decomposed during the same heat treatment. And both of the heat treatments would dehydrate the test specimen. And the observations for that were made using the machines on the right, the scanning electron microscope, the X-ray powder diffraction, and the Fourier transform infrared spectroscopy.
For the findings, dehydration results in the decreasing of all measured thermal and mechanical properties in the paste. The compressive strength decreases with an increase of water to cement ratio and increases in graphite content up to 1% graphite by mass, and then decreases as the graphite content approaches 15%. The thermal conductivity decreases as the water to cement ratio increases and the graphite content decreases.
For the volume heat capacity, we can see that the volume heat capacity increased as the water to cement ratio decreased, but then inversely increased as the graphite content increased. And then for the thermal expansion coefficient curves, we can see that the untreated samples were pretty unstable for lower temperatures, and then they were more stable for heat-treated samples at any graphite concentration. And then so we can conclude that the heat treatment creates more stable pastes, but then if you wanted a more unstable or not heat treating sample, it would lead to more unstable applications. The stabilizing factor for untreated pastes was around 300 degrees Celsius, where the evaporation of the chemically bonded water would stop and therefore make it more stable.